Think of an electrical circuit as a continuous delivery route. The battery acts as the loading dock, packing energy into passing charges, a process we call electromotive force, or EMF. Those charges travel the wire and drop their energy off at components like this light bulb. The energy deposited at the component is the potential difference. Both of these transfers are measured in volts. Mathematically, voltage is simply the amount of work done, or energy transferred, divided by the charge passing through. 1 volt equals 1 joule of energy per coulomb of charge. The speed of this delivery system is the current. It measures the exact amount of charge passing a single point in the wire every second. If you have a high rate of charge flowing over time, you have a high current. Due to a historical naming error, we actually track 2 different directions. The free electrons themselves physically flow from the negative terminal to the positive terminal. However, the standard model we use for circuit diagrams, conventional current, is always drawn pointing the opposite way, from positive to negative. Tracking how energy is loaded and how quickly it flows gives us a snapshot of the circuit's state. But to understand the behavior of the whole system, we need to look at how the physical components themselves interfere with that flow. A wire doesn't let current flow perfectly freely. Just like a narrow pipe restricts water, a conductive material restricts the flow of electrons. This restriction is resistance, and Ohm's law defines it as the ratio of voltage to current. The physical shape of the wire directly controls this resistance. If you double the length of the wire, the charges have to push through twice as much material. The resistance doubles. They are directly proportional. But if you widen the wire, giving the charges twice as much cross-sectional area to travel through, the flow becomes easier. Doubling the thickness cuts the resistance exactly in half. They are inversely proportional. Tracking direct and inverse proportionality can create some tricky math scenarios on exams. If you find yourself stuck on a calculation, you can drop the problem to our 24/7 WhatsApp tutor for an instant breakdown. The physical geometry of the conductive path dictates exactly how much energy is required to push a charge from point A to point B. When you connect components in a single continuous loop, you create a series circuit. Because there are no alternative routes, the exact same current flows through every component. To keep that current moving, the battery's total voltage has to split, dropping incrementally across each resistor. A parallel circuit splits the pathway. The charges arrive at a junction and divide, meaning the current drops across individual branches. But because each branch connects directly across the battery's terminals, every single pathway receives the full, identical voltage. Calculating resistance depends entirely on your layout. In series, every new component is a new obstacle in the only available path. You simply add the resistor values together, and the total resistance climbs.
In parallel, the math flips. By adding a new parallel branch, you provide the charges with a completely new avenue to travel. Even if the new resistor is highly restrictive, having an extra path makes it easier for the overall current to flow. The total circuit resistance goes down. This behavior is exactly why modern electronics and household grids rely on parallel wiring. You can activate a TV, a microwave, and your lights simultaneously, without stacking resistance to the point where the entire system grinds to a halt. Standard resistors have fixed values, but sensory resistors adapt to their surroundings. The light-dependent resistor, or LDR, reacts to brightness. The thermistor reacts to heat. They both operate on an inverse relationship. As the environmental intensity goes up, more light or higher temperatures, their resistance values drop sharply. We use these components to build potential divider circuits. This layout features an input voltage passing through 2 resistors in series. We then attach a voltmeter across just one of those components, in this case the thermistor, to measure our output voltage. Remember the rule for series circuits. The voltage splits. The component that provides the highest share of the total resistance will take the highest share of the voltage. Let's test this logic. Pause the video. If the environment around this circuit suddenly becomes freezing cold, what happens to the resistance of the thermistor? And based on that, what happens to the reading on Vout? Successfully predicting a potential divider comes down to tracking the sequence. You move from the environmental change to the component's resistance shift, and finally to the meter reading. Let's trace the steps. First, the temperature drops. Because of the inverse relationship, the thermistor's resistance goes up. Second, we apply the series rule.
The thermistor now holds a much larger percentage of the circuit's total resistance. Because it holds more resistance, it commands a larger share of the input voltage. The V-out reading increases. When charges push through resistance, they do work. This work is released as internal thermal energy, which we often see as heat. If the current surges high enough, that heat can damage the circuit. To prevent this, we install a fuse, a deliberate weak point designed to melt and break the connection before the rest of the system fails. This open gap stops the flow of charge immediately. If tracking those voltage splits or working through safety logic still feels confusing, our 24/7 WhatsApp coach can walk you through detailed step-by-step examples until it clicks. Master this cheat sheet. Knowing your 3 core equations, the structural rules for series and parallel circuits, and the inverse behavior of your sensors gives you the tools to break down any schematic. To lock these concepts into your memory, visit www.studybuddy.tech and take our free diagnostic test. It will identify exactly where you are losing marks, so we can generate a customized study plan to get you ready for your final exams.